So here's the thing that keeps me up at night, and I mean that in a semi-literally way because I read about it before bed and then just laid there. We're building artificial intelligence at a pace that's genuinely staggering, and almost nobody is talking about the boring physical problems sitting underneath of it. Power. Not money, not chips, not talent. Electricity, the actual stuff coming out of the wall. Every time you ask a chatbot a question, somewhere in a windowless building the size of a few football fields, a wall of graphics chips light up, gulp electricity, and then dump out a colossal amount of heat that then has to be cooled, which takes even more electricity. And the demand curve for this is going almost straight up. At some point, the grid simply can't keep feeding the machine. People in the industry call this the power wall, and right now it's less of a wall and more of a cliff we're all sprinting towards. Which brings me to a small company in Austin, Texas called Neurophos. And I have to be honest with you, when I first dug into what they were doing, my reaction was somewhere in between that can't possibly work and wait, why isn't everybody doing this? Because their answer to the power problem isn't just a better electronic chip. It's to stop using electrons for heavy lifting entirely and use light instead. Let me back up and explain why this matters, because the whole thing clicks into place once you understand what an AI chip actually spends its day doing. Running an AI model is, at its core, a giant pile of multiplication. Rows and columns of numbers getting multiplied and added together over and over billions of times. Estimates put it at around 90% of the work involved in AI inference, which is just a fancy word for the model actually answering you. Now, here's the dirty secret of modern chips. The actual math is cheap. The expensive part is moving the numbers around. Your chip has to constantly shuttle data back and forth between the memory where the numbers live and the little engines that do the multiplying. And that shuffling, that endless commute of data across the chip is where most of the energy gets burned. People have tried clever fixes. One popular approach is analog electronics, where instead of crunching ones and zeros, you let the physics of the circuit do the math directly. That genuinely helps with efficiency, but it runs onto its own problem when you try to make it big. There's an effect engineers call RC delay, and the short version is that your electronic array gets larger, the signal starts dragging and smearing, like trying to send a clear message down a longer and longer wet string. When you do this kind of math with light instead of electricity, the physics works in your favor in a way that feels almost unfair. With an optical system, the power you spend scales with the perimeter of the array, the edge of it, but the actual computing throughput scales with the area, the whole surface. So the bigger you build an optical processor, the better it gets on both fronts at the same time. More speed and more efficiency together as you scale up. The CEO of Neurophos, Patrick Bowen, basically said that this is the rare trick you can only pull off with optics because analog electronics usually forces you to trade one for the other. That right there is the whole pitch. Light doesn't suffer the same delay problem electrons do over distance. Photons are faster, they generate very little heat, and they don't care much about temperature swings or electromagnetic noise. On paper, light has always looked like the obvious winner for this kind of math. So why hasn't anyone been computing with light this whole time? Because there's always been a catch, and the catch was size. The components you need to control light on a chip, the optical modulators, have traditionally been enormous compared to transistors. Bulky. You could only fit a handful on a chip, and a handful is useless when you need to multiply millions of numbers. Optical computing has been the technology of the future for decades, and it kept staying in the future precisely because the parts were too fat to scale. Neurophos' answer comes from a genuinely wild place. The core technology traces back to research at Duke University on metamaterials, the exotic engineered surfaces originally developed to bend light around objects, the stuff of actual invisibility cloak experiments. And here's the number that made me sit up. These metasurface modulators are roughly 10,000 times smaller than traditional photonic modulators. 10,000. That's not an improvement, that's a different universe. Each little element sits on a pitch of about 5 microns, and they can pack more than 1 million of them onto a test chip that's just 5 millimeters by 5 millimeters, a fingernail-sized square holding over 1 million optical computing elements. That density is the unlock. Suddenly you can build an optical tensor core that handles 1,000 by 1,000 matrix in one shot, where the best electronic designs are working with much smaller blocks and constantly splitting big problems into pieces. Not having to chop your matrix up and stitch it back together is, by itself, a massive efficiency win. And because it's built to play nice with standard Silicon Foundry tools, stacked in 3 dimensions and packaged right alongside the regular CMOS chips at high bandwidth memory, it's not some lab curiosity that needs an entirely new factory. It's designed to drop into the data centers we already have. Okay, let's talk performance because this is where it gets spicy. Neurophos' first generation optical processing unit, which they've nicknamed the Tulkas, is projected to deliver 235 peta operations per second while drawing 675 watts. To give you a yardstick, they compare that directly to Nvidia's B200, the current heavyweight champion of AI chips, which delivers roughly 9 peta operations per second at around 1,000 watts. So, the Neurophos part is putting out something like 26 times the raw output while sipping less power. The energy efficiency lands in the range of 2 to 300 operations per watt, and that figure already includes all the unglamorous support hardware around the optical core and the converters and interconnects that usually quietly eat your power budget. And the roadmap goes even further. Their stated long-term ambition is to eventually pack the equivalent of around 100 GPUs worth of work into the power envelope of a single core. Read that again. 100 to 1. If that even half lands, it doesn't just bend the power curve, it snaps it. Now, I want to be measured here because these are projections from a young company and the production chips aren't out yet. But the prototypes are real and they're being demonstrated to customers in Austin right now. And that money behind it is not the kind that shows up from Vaporwave. This past January, they closed a $110 million round led by Bill Gates' Gates Frontier Fund, with Microsoft's venture arm, Bosch, and Aramco's investment group all climbing aboard. A Microsoft technical fellow went on record about the monumental power and compute that modern AI inference demands. And when that crowd writes checks together, they've kicked the tires hard. Now, I'd be doing you a disservice if I pretended that this is a done deal. It isn't, and there are 3 real mountains to climb. The first is software. Nvidia's true moat isn't just its chips, it's CUDA, the programming ecosystem that millions of developers already know and rely on. Neurophos has to give people a way to use this hardware without rewriting their entire world, and they're smartly building on top of the open tools like PyTorch and Triton rather than asking everyone to learn something exotic. They even acquired a small chip IP company to grab a programming model similar to what GPUs already use. Smart, but it's still a hill. The second is manufacturing yield, the eternal nightmare of anyone making chips. Demonstrating something brilliant on a test wafer and cranking out millions of reliable units are 2 very different sports. And the third is simply scaling the whole architecture up while keeping all those promises intact. Production isn't expected until somewhere around 2027 or 2028, so there's a long road still. But here's where I land, and I'll just say it plainly. I'm I'm rooting for this, and not naively. What I love about the Neurophos approach is that it isn't fighting physics. It's recruiting physics. Instead of squeezing the last drops out of an electronic design that's clearly hitting its limits, they found an angle where getting bigger makes everything better instead of worse. That's the opposite of the trap everyone else is stuck in, and it's genuinely fresh way to think about the problem. If they pull it off, computing with light stops being the forever promise of tomorrow and becomes the thing quietly running your AI tomorrow morning. And the cliff we're all sprinting towards, it might just turn back into a wall with a door in it. I, for one, can't wait to see if the light gets through.